Hi, in this video, we are going to continue our discussion of number theory. Today, I want to talk about primes. Okay, so we know basic facts about prime numbers that they are infinite in number and there are arbitrary large gaps between primes and so on. What I want to talk about is certain theorem and its proof and the techniques that we use in that proof because that will be useful later on as we see more and more problems. So the theorem that I want to state is this. There are infinitely many primes. There are infinitely many primes that are congruent to 3 mod 4. So basically the theorem is saying that there are infinitely many primes of the form 4k plus 3 or 3 mod 4, right? So the standard proof of this goes like this. We do a proof by contradiction. We'll say, suppose there are only finite number of primes congruent to 3 mod 4. And since there are only finite number of primes congruent to 3 mod 4, let's list them out. Let's list them out and let's say those primes are in this list. Starts off with 3, then we have P1, P2, and it goes on till PR. So basically this is the finite list of all the primes of the form 3 mod 4, right? Now our goal here is to find a new prime Q that does not lie in this list and is also a prime of the form 3 mod 4, right? Because if we can find a new prime by some process, then we can say that we'll have to add Q to this list. And if that process is repeatable, then we can repeat the process infinite number of times to show that every time you can make a new prime, and therefore the number of primes which are 3 mod 4 must be infinite, right? So how do we achieve this? So what we will say is this is my initial list of primes which is 3 mod 4. Now consider the number A. We are going to take a number A which is of the form 4, P1, P2 till PR plus 3. Notice here that I have not included 3 in the initial product here. The product is of P1, P2 till PR multiplied by 4 plus 3. So this number A can be factored into prime, and let's say A has a prime factorization like this. A is equal to Q1, Q2 till Q of S. All of these Q1, Q2, Qs are all prime numbers. Now I will make certain claims now. So I will just write it here. A is equal to 4 P1, P2 till PR plus 3 and A has been factorized as Q1, Q2 till Qs. The first claim that I want to make is that among primes Q1, Q2 till Qs, there is at least one prime which is 3 mod 4. Why is that so? Suppose there is not a single prime which is 3 mod 4 here. So obviously if not a single one of them is 3 mod 4, then all of them are 1 mod 4, congruent to 1 mod 4. But what will that ensure? If all of the primes are 1 mod 4, then the product of the primes A is also 1 mod 4, right? If every prime here is 1 mod 4, the product becomes 1 mod 4. But we have here A was defined like this, and A is clearly 3 mod 4. So that means there is a contradiction between these two statements. That means all of the primes here cannot be 1 mod 4. Therefore, at least one of them must be 3 mod 4. So my claim 1 is correct. And so we'll say that let's say let Qi be the prime which is 3 mod 4. Right? Now what is my claim 2? Claim 2 says that Qi is not in the original list of primes. Qi is not in the original list of 3 mod 4 primes. Of 3 mod 4 primes. The original list, if you recall, was 3 P1 P2 till PR, right? What I want to say is that Qi does not exist in this original list. Why can I say this? Because from here, it is obvious that Qi clearly divides A, right? Qi is a prime factor of A. However, you can see that none of the primes here divide A, right? Any prime here, P1, P2 and all, they don't divide A because they might divide this initial factor, but they don't divide 3. And 3 does not divide this, right? Because it's a collection of primes and 4 is just 2 square. So none of the primes here in this original list divides A, but Qi divides A. Therefore, Qi is not in the original list of 3 mod 4 primes, right? And therefore, Qi, we have realized that Qi was itself a 3 mod 4 prime, so Qi must be added to the list, must be added to the initial list of 3 mod 4 primes, right? So we have discovered a process by which we started out by saying that initially my finite list of 3 mod 4 primes was 3 P1 P2 till PR. But now we are getting a new Qi which is not part of the original list, which must be added to the list, right? So that means that if I repeat this process endless number of times, I will be able to extend that list forever and ever, right? And therefore, we have proved that the number of 3 mod 4 primes is infinite, correct? Notice that the same method that we have done here won't work for 1 mod 4 prime. So if I want to prove that the number of 1 mod 4 primes is infinite, and if I try doing this by creating a list of 1 mod 4 primes, for example, P1, P2 till PR, and let's say I do the same process. I create a number here, 4 times P1, P2 till PR plus 1. This number is itself 1 mod 4, and we say that it must be a factorization of some prime numbers Q1 to Qs. The problem is in this step, we cannot be guaranteeing, we want to find a Qi here that is 1 mod 4, right? But that is not guaranteed because it is possible, to take two 3 mod 4 primes and multiply to get a 1 mod 4 prime. Multiply to get a 1 mod 4 number like A. For example, if you take two primes 3 and 7, these are both 3 mod 4 primes, but when you multiply you get 21, which is 1 mod 4. So if my A is 1 mod 4, it doesn't guarantee that there has to be a Qi here which is 1 mod 4, right? Because all of the Q's could be 3 mod 4, and it could turn out to be a case like this where product of 3 mod 4 primes is giving a 1 mod 4 number. So basically what we are saying is that the method that we used in the previous example does not work here, right? So we cannot use the fact that A is 1 mod 4 to deduce that some prime factor of A must be also 1 mod 4. However, we could have done that for 3 mod 4 case. So if A was 3 mod 4, we can deduce from there that some prime factor of A must be 3 mod 4, right? Okay. Now we come to the next idea for this class, which is Dirichlet's theorem. This is an important theorem. The statement of the theorem is this: let A and M, let A and M be integers such that the GCD of A and M is 1, then there are then there are infinitely many primes that are congruent to A mod M. So basically, just like we did earlier, we proved that there are infinitely many primes which are congruent to 3 mod 4, right? We have done the proof of that. We claimed that there will be infinitely many primes which are congruent to 1 mod 4, but we did not have a proof for that, right? What Dirichlets theorem ensures is as long as A and M have GCD 1, there are infinitely many primes that are congruent to A mod M, right? Here, this is my A and this is my M, right? The GCD of 3 and 4 is 1. So by Dirichlets theorem, we can confirm that there are infinitely many primes of this form. Now, the proof of Dirichlets theorem is too advanced and we'll not be able to do it right now. Excuse me. It basically involves concepts from complex analysis. So we won't do the proof here, but understand that the idea is similar to what we have already proved. We have proved the case of 3 mod 4. That is a special case of Dirichlets theorem. Now let's see something else here. For example, let P be an odd prime. Let P be an odd prime, and we write 1 plus half plus 1 by 3 and so on till 1 by P minus 1 as a fraction AP by BP in the lowest terms. So what I want you to think about it, you want to write this sum of terms as a fraction AP by BP and then reduce it to the lowest terms. What I want you to think about it, find the value of AP mod P and also try to think about what is AP mod P square. Okay. So think about this structure here, and you can realize first of all that since the number of terms here is even. Why is the number of terms even? Because P is odd, since P is an odd prime, and this goes from 1 to P minus 1. So there are even number of terms here, right? So you can always try and group these terms together in this way. You can say I will always be able to find a term 1 by k here and also a term 1 by p minus k here. And if you group them together, what will happen? You will get 1 by k plus 1 by p minus k, which will be equal to p by k times p minus k, right? So notice that the numerator is looking like it will be divisible by p, right? When you add these two terms, the numerator is divisible by p. When you take any other grouping like that also, you will get again numerator will be divisible by p. So we can predict here that this should be 0. AP mod p, AP is the numerator upon adding, right? It should be 0. Now let's test it out for a few cases. For example, let p be an odd prime. So let's say p is 5. Now think about it. What is the expression? 1 plus 1 by 2 plus 1 by 3 plus 1 by 4. We had to go till p minus 1, right? So this is my expression. Now let's group it together nicely. So we'll say 1 by 1 plus 1 by 4 together and 1 by 2 and 1 by 3 together. So this becomes basically 5 by 4 and this becomes 5 by 6. And now when you add these, you get 5 into 3 plus 5 into 2 by 12. So that is becoming 5 times 3 plus 2, 5 by 12, right? So you're getting 25 by 12, and notice that the AP is 25 and 25 mod 5 is 0. So basically what you are getting is AP is congruent to 0 mod P, right? By the way, you can test it out for different prime. If prime P is greater than equal to 5, you have the sequence. You have the sequence like this till 1 by P minus 1. We can also say that this is equal to AP by BP. It is possible to prove that if prime P is greater than equal to 5, then AP is congruent to 0 mod P square. We have already seen that AP is congruent to 0 mod P, right? We can also show that AP is congruent to 0 mod P square, and actually that is true for only primes greater than 5, and this is a statement of Wollstonholm's theorem. So we will not do the proof, but you can confirm it yourself that this works out to be true, right? One last thing that I want to discuss today is this idea. What is the highest power of 2, for example, highest power of 2 in the numbers, let's say 1 factorial, 2 factorial, and so on, right? So what we want to find out is highest power of a prime P in a number capital N, right? You can show that this highest power of a prime P, let's denote it by the symbol VPN. This tells us the highest power of prime P in the number N, right? N factorial. I missed saying that. Obviously, the number N we can simply factorize. So I want to find the highest power of prime P in N factorial, not just N, because that would be trivial. So let's denote this by VP N factorial. And what you can show is that that will be equal to N by P GIF plus N by P square plus N by P cube. And you keep doing these sequence of GIFs. So you can write this like this. K goes from 1 to infinity, GIF of N by P power K. Notice obviously that when P power K becomes greater than N, the GIF will automatically vanish. GIF tends to 0 because it will become a fraction less than 1, right? So this is equal to VP N factorial. You can verify this result for any value of N and P. The idea is that suppose we take 5 factorial. 5 factorial is 5 into 4 into 3 into 2 into 1, right? Now, if I want to find V2 of 5 factorial, right? So what I will do is I will say it is GIF of 5 by 2 plus GIF of 5 by 4 plus GIF of 5 by 8, and all will vanish. So 5 by 2 will give us 2 and 5 by 4 will give us 1. Notice how it is coming. When you take powers of 2, the first power of 2 will appear in all the even numbers, right? So you'll get 1 power of 2 here, 1 power of 2 here. But when you look at power 2 square, you will get 1 additional power of 2 here, right, from here. So therefore, the second term here tells us how many additional powers of 2 you're getting. So this formula definitely works. Now, an extension of this is an inequality idea. So you should be aware of this as well. So prove that if P is a prime and if P power m divides n factorial, then there is an inequality. M is less than n by p minus 1. So think about it. If p power m divides n factorial, he is saying that m should be less than n by p minus 1, right? We know that GIF of x is always less than equal to x. So since Vp of n factorial was equal to GIF of n by p plus GIF of n by p square, GIF of n by p cube, and so on, think about it. This is going to be a set of finite terms, right? This is a set of finite terms because even if the series extends till infinity, most of the other terms, when p power k is greater than n, most of the other terms are going to become zero because of the GIF function, right? So therefore, what we can say is only finite number of terms here will add any value to the Vpn function, right? So we can say Vpn factorial will be less than n by p plus n by p square plus n by p cube and so on. Because this is an infinite series, and we know that GIF of each term is less than equal to x, right? So we are removing the GIF and saying this inequality. Anyway, it's an infinite series. We can do the sum of an infinite series. So therefore, we get Vp n factorial is less than n by p was the first term, and 1 minus 1 by p. 1 by p was a common ratio. So this becomes n by p times 1 minus 1 by p, which is equal to n by p minus 1. So we are getting Vp n factorial is less than n by p minus 1. And we knew that p power m divides n factorial. So m is equal to Vp n factorial, right? So we get m is less than n by p minus 1, which is the inequality that we wanted to prove. And remember this inequality because we'll be applying this inequality in problems in the future. So this is an interesting inequality. It will be useful several times in the future in problems. Okay. So keep that in mind. So that was it for the short video today. Uh, we are discussing primes. In the next class, I will try to do the theory for how you raise powers modulo m. So we will learn about powers modulo m and by the method of successive squaring. So we'll do that in the next class. And we'll also have a few problem solving sessions in between. So I'll see you next time.